how to harness energy from nuclear fusion, how to heat treat a superconducting coil which measures 4 meters in diameter, 2 meters tall, and weighs 110 tons. And it has to be done with accuracy of plus minus 10 C. These and many other questions will be answered during my presentation today. Obviously, I am not relying on myself to provide you all the answers. I have 3 special guests today. We have 2 guests in San Diego, California. Mr. Kenneth Kamtong, who is the technical lead for the final testing and fabrication of ITER CS magnets at the General Atomics Magnet Technology Center. And we have Mr. Nikolai Narowski, who is a program manager with mechanical engineering background, and he's a member of General Atomics Magnet Technology Center since 2011. In Świebodzin, Poland, we have Artur Banaś, who has been with SICO Warwick since 2004. Artur is a very experienced service engineer, and he is currently Deputy Service Manager at SICO Warwick SA. My name is Rafał Walczak. I'm a Product Manager at SICO Vacuum Technologies here in Meadville, Pennsylvania. Welcome. We have a big project to discuss today, and we will be talking about ITER, a global R&D project which is focused on development of new energy sources. We will demonstrate what is our input into ITER project, and we show how big R&D projects energize the industry and initiate new developments. Finally, we will explain what special safety features have to be implemented in order to ensure safe heat treatment of weighing 110 tons product during 5-week long heat treatment cycle. But first, let's see what's ITER, how is it made, and why is it so important for future human population. We'll find answer to these questions in the following video provided by company General Atomics, our customer and partner from San Diego, California.
This is ITER, the largest science experiment ever built on Earth. This massive facility under construction in Cadarache, France, is being built by a global coalition of 35 countries. Its mission is to demonstrate the feasibility of fusion as an inexhaustible source of energy for the entire planet. At the heart of the ITER device will rest the central solenoid. It will be the largest pulsed superconducting magnet ever built. It will drive more than 15 million amperes of current into the fusion plasma to heat and stabilize it. The 6 modules of the solenoid are being fabricated at this facility in San Diego by General Atomics, under the direction of the U.S. ITER Project Office. GA is a recognized supplier of high-tech hardware with decades of experience in fusion research. Here at GA's Magnet Technology Center, a skilled team of technicians and engineers are hard at work producing the 59 feet tall central solenoid, along with a 7th module that will serve as a spare. Inside the facility is a highly specialized purpose-built production line for fabricating and testing the central solenoid modules. When the team at GA took on the central solenoid project, they faced a series of challenges, starting with modifying the facility to accommodate the 250,000-pound modules. The standard floors were replaced with 24 inches of concrete to support that weight, while cranes and other specialized infrastructure were added to support the manufacturing process. The core challenge was how to build the machinery and processes needed to form 3.6 miles of steel-jacketed conductor into a 40-layer module with 14 turns per layer. Years of careful engineering and design efforts, in close collaboration with experts across the globe, yielded a 10-step fabrication process that pairs the latest technology with highly trained technicians to produce the modules. The production of a module requires 2 years, followed by months of testing. The process begins with delivery of spools of conductor from Japan, part of that country's in-kind contribution to ITER. One of the earliest and most complex steps involves the precise winding of the conductor to create the turns of each module. The conductor must first be almost perfectly straightened from the spool, then bent by rollers exerting immense force to shape the individual turns into precise radii. Because the conductor lengths are limited to 900 meters, modules cannot be made from one continuous piece of conductor, but are instead made from 7 sections that must be joined together. The team has developed an innovative process to bring together lengths of conductor into a seamless joint. First, the stainless steel jacket is machined away from the 864-strand cable of niobium-3 tin and copper wires. The strands of the cable have to be spliced together before a highly skilled operator uses a computer-controlled process to weld the stainless steel jacket over the splice. To create its immense magnetic field, 50,000 amperes of current must be driven in the central solenoid module. For this, the module must be superconducting. However, superconducting material is brittle and cannot be bent. This means conductor wires start fabrication in metallic form before being converted into superconducting ceramic-like material by a 5-week heat treatment process. During the heat treatment, the module is heated at temperatures over 1,000 degrees Fahrenheit for more than 14 days, after which it is slowly cooled for a week to complete the process. To keep the electrical current in the conductor, every inch of the steel-jacketed superconductor must be wrapped with 6 layers of electrically insulating tape, a total of 180 miles per module. To protect the now brittle superconducting material from damage, GA built a massive machine to lift the 250,000-pound modules off the ground. Each turn is then separately released to stretch them like a slinky, making room to apply the 6 layers of tape. But the team is still not done. They must wrap the surfaces of each module in additional layers of insulation, ensuring the coil is electrically protected from EATER and EATER is protected from the coil. The next challenge is to convert the 560 turns of the coil into a monolithic structure to withstand the immense forces it will be subjected to during the operation at the center of the EATER device. With a mold placed around the coil, all the air is sucked out and replaced by 900 gallons of resin, which completely fills all spaces in the module. The resin is then cured at 260 degrees Fahrenheit. Once the module completes fabrication, one final step remains, and this one is perhaps the most grueling. The magnet must be tested in EATER-like conditions to ensure it will function as planned. It is placed in a special test chamber where it is cooled in a nearly complete vacuum to 4 degrees Kelvin or minus 460 degrees Fahrenheit. After months of intense tests, the module is certified ready to take its place in the heart of EATER. The first central solenoid module finished testing in 2020, paving the way for remaining modules to follow to the EATER site over the next 2 years. The module is placed on a shipping fixture, boxed up, and trucked to a port in Texas, where it's loaded onto a ship for its journey to France and the EATER site. Once all the modules are stacked and surrounded by supporting structure, they'll be lowered into the center of the massive EATER tokamak, forming the beating heart of this historic effort to fulfill the promise of fusion, the promise of unlimited energy for all of future humanity.
Central solenoid magnet is installed in the heart of EATER. As it was said on the video, solenoid coils require special thermal processing, called reaction heat treatment. Sika Warwick had the opportunity to design one of the world's largest vacuum furnaces in the history and installed in General Atomic Magnet Technologies Center to fulfill these requirements. So Ken, what is the central solenoid magnet?
The central solenoid magnet is made up of 6 individual modules stacked on top of each other. When completed, the entire stack is over 5 stories tall and weighs nearly 1,000 tons. Each module starts as niobium-3 tin conductor, which is wound into a solenoid shape, 14 turns deep and 40 layers tall. Nearly 6 kilometers worth of conductor goes into each module. After winding, we heat treat the modules over the course of 5 weeks at temperatures as high as 650 degrees Celsius. What that does is it transforms the properties of the conductor such that it's now superconducting. This allows the modules to conduct very high electrical currents, which in turn generate very high magnetic fields. These fields help to shape and contain the plasma at the core of the fusion reaction, which can burn as hot as 100 million degrees Celsius. To put that a bit into perspective, that's about 10 times as hot as the surface of the sun.
We've just heard what central solenoid magnet is and what it does to the fusion reactor. As Ken mentioned, the magnet is made of 6 modules, which altogether weigh nearly 1,000 tons. Nikolai, can you please help us understand how each individual module is designed and how it is produced?
Each one of our CS modules is over 4 meters in diameter, 2 meters tall, and weighs 110 tons. It's made up of 6 kilometers of superconductor in a stainless steel jacket. The conductor has to be wound in a very precise pattern of 560 turns, and those turns have to be set down in the right position within 0.5 millimeter. At the very end, the two ends of the magnet that provide all the electrical current to the magnet have to be positioned within 10 millimeters after 6 kilometers of length. When the magnet is running at its operating temperature of about 4 degrees above absolute zero, the superconductor has no electrical resistance. That means it can handle the 40,000 amps required in order to generate the magnetic field. The cable does not start out as a superconductor though. It starts out as individual strands of copper, niobium, tin, and a bronze or tin alloy. And it has to go through a very specific heat treat process in order to allow those elements to fuse together and make the superconductor.
Someone finally said the magic word, heat treatment. So what is special about our reaction heat treatment process?
The process that we use involves using fans inside of our convection furnace to force pure argon around the module to slowly and uniformly heat it up and allow the superconductor to form. The module is ramped up in temperature to 570 degrees Celsius, where it's held for about 10 days. After that, we ramp it up to 650 degrees Celsius, about 1200 degrees Fahrenheit, and it's held there for 4 additional days. The whole heat treat process takes 5 weeks.
5 weeks long heat treatment process is very unusual for most of our viewers. But what about process requirements and temperature uniformity within 6 kilometers of conductor?
The temperature inside the furnace has to be ramped very slowly and controlled at 5 degrees C per hour. And the uniformity of the module is watched very carefully. No two spots in the module are more than 20 degrees Celsius apart from each other.
Were there any other precautions taken to ensure proper environment for reaction heat treatment?
Before and after the heat treat process, we fill the magnet with helium to about 3 megapascals or 435 psi. That allows us to check the conductor for any leaks before and after the process. During the heat treat process, we monitor the purity of the argon that's flowing around the module to check for any contaminants or volatile compounds that might damage the superconductor. When the process is complete, the conductor now contains 2 strands of superconductor for every 1 strand of copper. And from that point on, the superconductor is very brittle, and we have to take extra precautions not to damage it in our manufacturing process.
This is a very conservative approach, but as we remember, we have 110 tons of precious load in the furnace, and the thermal treatment takes 5 weeks. Very serious task. Thank you, Nikolai, for explaining the reaction heat treatment process to our viewers. Ken, would you please explain what are the next steps in manufacturing of CS modules before they are shipped to ITER site in France?
After heat treat, we insulate the modules with nearly 300 kilometers of insulating tape and fiberglass. And then the entire module is encased in nearly 1,000 gallons of epoxy resin. What this does is it locks the conductor and insulation together to create one monolithic structure, able to withstand the immense magnetic forces inside the reactor. Finally, we run a battery of tests on each and every module, subjecting them to voltages as high as 30,000 volts and powering them with as much current as 40,000 amps. This is done to ensure that every module meets all of ITER's specifications prior to shipping them out to France.
This is impressive. We are so proud to be a partner of General Atomics on this project. Thank you, Ken and Nikolai, for explaining how our vacuum furnace can help the world and support research and development of new energy sources. Now, I would like to focus your attention on the furnace. As I already mentioned, especially for this project, Seco Warwick designed and delivered one-of-a-kind, record-breaking vacuum furnace. Arthur, as we could hear a few minutes ago, Nikolai mentioned about very tight temperature requirements during reaction heat treatment. We already heard about extremely heavy load, weight, and load dimensions. How do we control temperatures throughout the process? How many control zones are there in the furnace? How many control thermocouples? And so on.
Typically, furnace have 1 up to 3 maybe. Okay, this is a standard. In this case, we have 12 heating zone. Each one have installed 4 control thermocouples. Why? Because first thermocouple take in the main work. If any failure, system automatically switch to the next one. This is the redundant system. And so on, If second have failure, switch to the third one. Third one, switch to the fourth one. Because the target was, when we start the cycle can't be stopped.
All right. Our customers often use load thermocouples to monitor load temperature during the process. How do we measure temperature within the CS coil during the reaction heat treatment cycle?
What do you think? Typically, how many thermocouples are used normally for the typical cycle? 2, 5, maybe 9. In this case, can you imagine it? We have 150 elements which have to be installed on the load. Huge work.
150, that's amazing. What are these 150 thermocouples used for? Are they recorded or just provide visual information for the operator? Please explain.
All thermocouples are connected to the system. So because of big load, huge load, that's why requirements from the customer was all of them have to be connected. I have to be in the real time, have to monitor temperature during the ramping and soaking time.
Just a minute ago, you mentioned that once the process is started, it may not be interrupted by any minor errors. Why is it so important?
Why cycle can be stopped? I will give you the answer. The preparation of the load before we put the load into the furnace takes 1 month. So 150 thermocouple installed on this big huge load take a long time. And the next month, so remember 1 month, this is another step for the cycle. So in this time period, 1 month for the preparing and 1 month for the cycle, we can't say, okay, we should stop in any problem. No.
You're saying 1 month of preparations before the process? Why does it take so long? Can we just close the furnace and push the start button to go?
Typically in the furnace, we open the door, put the load, close the door and start cycle. But not this time. Here the steps before start cycle, when the load is inside, so was already prepared, it's totally different. When the operators sit down opposite the computer, the first, like you will install any software in your computer, step by step check every subsystem, starting from the pumping and finish that everything is working good. There is a time to start real cycle.
Okay, so what happens if the operator forgets one of the steps in this sequence? Does he have to repeat several weeks long procedure?
All the steps which are checked before starting the cycle, if one of them will get negative result, means something will not working correct, system will not allow to go forward, means make step to the forward and jump to the next subsystem. So all have to be completed with positive result, and then system will unlock button to start real cycle.
When the process lasts over a month, 5 weeks to be exact, it may happen that the operator is away from the furnace for any reason. Were there any special features added to allow remote alarming and diagnostics?
There is nothing special. Today, here, in all of the world, so all the machines have this kind of connection. But what is interesting here on this project, in case when alarm appear on the computer, at the same time, this information is sending for 2 dedicated mobile phones. Because, as we say on beginning, the point was the cycle never can be stopped.
Artur, thank you for explaining to our viewers what special measures were taken in order to maximize safety of the operator, safety of the load, and safety of the equipment. Our furnace was installed and commissioned at General Atomics plant at the end of 2014. We all know that there is always steep learning curve when the new unique piece of equipment starts to run production of unique, almost prototype parts. Now I would like to ask Nikolai what has been accomplished since then and how the equipment performed.
The Seco Warwick furnace has been proven to be very reliable and robust. To date, we've done 6 of the 7 heat treatment cycles for our CS modules, and in the coming months, we'll do the 7th and final cycle. In all of those runs, we have not had any problems during the operation. Seco Warwick did a great job designing in backup systems and robust design. And anytime we had questions or needed maintenance, they were there to help. They even helped us upgrade our control system based on lessons we learned in the operation. The crew that Seco Warwick sent out was very professional, very hardworking, very knowledgeable, and had great positive attitudes. They were definitely one of the favorites of the staff here.
Thank you, Nikolai. It is very nice to hear such nice compliments about our team and about our equipment. And Artur, would you like to add anything to what Nikolai just said?
During my career here, I was involved for many projects, but because of the technical, the highest level, here this project will stay in my mind till probably end of my life. So from the technical point of view, and from the place where furnace is located, because it's San Diego, California.
Thank you, Artur, for the comment. I know what you have in mind when you said San Diego. I saw that little smile on your face. I've been there several times and I always bring back good memories. Dear participants of our 2021 e-seminar, thank you for your attention and staying with us. I hope you enjoyed the presentation. Thank you, Ken, Nikolai, and Artur for your input. Also, special thanks go to Mr. John Smith, Director of Engineering and Projects at General Atomics, and his professional team. This would not be possible without their support. Thank you very much. Bye-bye.